Good evening, my name is Tony Peters. Today I have the Blackbody Radiation Simulator device, which is intended to subject a irregularly shaped photovoltaic array, which may be embedded onto airfoils, to analyze for differences in temperature, differences in humidity, vibrations, things of that nature as influencing factors to overall photovoltaic output in terms of volt and current and things of that nature. So what I've done is fabricated this device to subject an array of choice to all of those factors. What happens is typically I'll have a photovoltaic device embedded onto the surface of an airfoil. This is an LRN 1015, very similar to the MQ4C Triton UAS airfoil. And I just print out a cross section and I can induce a lot of different variables to it. These are kind of an example of the heating elements that I have because temperature is a very big player into photovoltaic performance. I'm using flexible polyamide PTC heaters, which are controlled through an independent temperature controller, which I'll show everything on the front end of here once I power it all on. So typically what will happen is it'll run through its warm-up process, boot up all these different sensors, and I'll kind of just go over what each of them does and what kind of data logging capability I have. Right here I have my thermal base plate, which is connected, to my environmental control monitoring subsystem. And then I have my photovoltaic array that I just talked about before. I 3D printed a lot of these models, and it's got the heating elements already embedded underneath the photovoltaic array. And I've got my artificial sun module subsystem there at the very top. Everything, all the brains and everything are right below this intake here, or this manifold. And what I'll do is I'll fire this up, get everything going, and then explain kind of what's going on. Lots of different fans, got to keep it nice and cool. So the artificial sun module subsystem is actually going to what I call a zeroize condition. Since it's emitting a specific wavelength of light through different beta angles, it needs to be consistent and make sure it's going to a zero condition. Okay, so my beta angle position and control system is normalized, and what I'll do is I'll put it right back up to the 90-degree position. Sometimes I accidentally only hit 40 steps instead of 400. So it'll go through its full sweep, zeroize, and then you can put it right back up to the 90-degree position. So what we'll do is we'll take a look at the interface. So you can close this up, and then you can take a look at all your data. So I talked about my beta angle position and control subsystem first, my BAPSYS for short. It converts steps from 0 to 800 steps into an angle resolution. Right now, I actually can get within 0.225 degree resolution for my beta angle analysis. I use this CNC device interface in order to actually conduct that base conversion or step to angle conversion. Right here, this is my environmental control and monitoring subsystem. It can log the base temperature, which is from the thermal base plate, the ambient temperature, both in degrees Celsius, the ambient pressure, and the humidity levels. All the red buttons typically are reset. This is my artificial sun module subsystem. It's built into 2 layers. The first layer is actually what emits all the wavelengths of light under specified wavelengths. And the second layer is actually what uses a time of flight sensor to give me distance to the PV in millimeters, the photovoltaic temperature, because it uses a contactless infrared sensor device, and it'll actually detect or give me the surface temperature of the ASMS itself to make sure there's not too large of a delta in terms of temperature. And then it's great because I can actually measure reflections in the UV spectrum and visible spectrum, and just to make sure I'm getting any kind of reflections based off of cover glass thickness and materials. One of the last ones down here in this column is my spectrum calibration and response subsystem. You want to know exactly what you're putting into the system so you can put this in there before you put the airfoil in to make sure you're getting what you're supposed to be getting. So I could get my visible and my IR intensity, my luminous flux intensity in terms of lux right there. I could get my IR and visible analog values so I could determine which percentage roughly of that total lux is attributed to IR or to the visible spectrum. Right down here at the very bottom, I have my ultraviolet spectrum in A and B And then you can even get a UV index. Good thing these are all 0 because we're inside. That would make sense unless we'll be getting a really good suntan. This can also be data logged. This system can also be data logged. It's my photocurrent measurement subsystem, and it can detect voltage, current, and power in whatever, and it can data log it and whatever I subject this to. So one thing I have here when I go back up is, like I talked about, the first layer of the ASMS. This is for a calibration laser. It's just supposed to make sure that you can turn it on and off. It's just a toggle function. But this allows me to know my system is ready to subject it through a series of wavelengths of light. It'll go between red, green, blue, white, ultraviolet, and IR, and then back to itself. And then what I can do here is subject it to red first, and then what I can do is use this switch down at the bottom with my PCMS. It's just a potentiometer, and it serves as a variable resistance to the photovoltaic array so that I can gain typical PV and IV curves by increasing that resistance. This right here is my temperature controller. Unfortunately, it's in degrees Fahrenheit, but I could just do some basic math and translate that. I could set it through an array of temperatures to control those hot spots that I was talking about and measure the difference. And between my spectrum calibration and response and my photocurrent measurements, I can log a myriad of data, both environmental and what the spectrum response is to the photovoltaic output. Then I can change it up. I can replace all the innards there with a different airfoil, like I talked about before, measure all the different responses and see exactly what kind of characteristic can be attributed to those irregularly shaped airfoils. For your consideration, again, my name is Tony Peters, and this is a Blackbody radiation simulator device. Thank you.